Mr. B here. For a simple reaction where reactant A produces product B, the rate may be calculated by dividing the change in concentration of reactant A by the change in time, or by dividing the change in concentration of product B by the change in time. However, for a reaction where the concentration of A is twice the concentration of B, or where 2 moles of A produces 1 mole of B, a different technique is required. In this video, I will explain how to use the stoichiometric relationships in a chemical reaction to calculate the reaction rate. Obviously, concentration is very important in determining the rate of a chemical reaction. Consider the following general equation, where A reacts with B to produce C and D. In this example, the lowercase letters represents the coefficients associated with each species. In other words, the molar ratio of this balanced equation would be A to B to C to D. To use these coefficients to determine the rate, simply take the reciprocal of each coefficient. For example, in this particular case, the rate would be equal to negative 1 over A times the rate of disappearance of A is equal to a negative 1 over B times the rate of disappearance of B, which is equal to 1 over C times the rate of formation of product C, and which is also equal to 1 over D times the rate of formation of product D. What if you wish to compare the rate of disappearance of reactant A to the rate of disappearance of reactant B? Simply set up an equality where the rate of disappearance of reactant A is equal to the rate of disappearance of reactant B. However, since reactant A and reactant B have different coefficients in the balanced equation, the fractions will also be different. Therefore, to compare the rate of disappearance of reactant A to the rate of disappearance of reactant B, simply solve the fractions. In other words, to clear the fraction associated with the disappearance of reactant A, simply multiply through by A over 1. The relationship between the disappearance of reactant A to the disappearance of reactant B is equal to A over B times the rate of disappearance of reactant B. As a practical application, let's consider the formation of ozone from oxygen gas. In this balanced equation, 3 moles of oxygen gas will produce 2 moles of ozone. The rate of this reaction may be written as follows. Rate is equal to a negative 1 over 3 times the change in concentration of oxygen gas divided by the change in time, which is equal to 1/2 times the change in concentration of ozone divided by the change in time. The rate of disappearance of oxygen gas to the rate of formation of ozone may now be written as follows, where the rate of disappearance of oxygen gas We know this is disappearance because the expression has a negative sign. The rate of disappearance of oxygen gas will now be equal to 3/2 the rate of formation of ozone. Now let's consider the following practice problem, where we're asked to write the rate expression for the following reaction in terms of the disappearance of the reactants and the appearance of the products. The rate expression for this particular reaction may be written as follows, where rate is equal to a negative 1/4 times the change in concentration of ammonia over the change in time, which is equal to negative 1/5 times the change in concentration of O2 divided by the change in time. For the products, we write is equal to 1/4, a positive 1/4 because the products are being formed. So we write 1/4 times the change in concentration of NO over the change in time. And finally, 1/6 times the change in concentration of water over the change in time. To determine the rate of disappearance of ammonia compared to the rate of formation of water, simply set up the following equality. From the information, the rate of disappearance of ammonia is equal to 2/3 the rate of appearance of water. To 2/3 was calculated from 4/6. 4/6 is reduced to 2/3. Suppose the rate of appearance of the water was found to be 6.5 times 10 to the minus 3 molar per second. What would be the rate of disappearance of the ammonia? In this case, the rate of disappearance of ammonia is equal to 2/3 the rate of appearance of the water. Therefore, by inserting the value for the rate of appearance of water, in this case 6.5 times 10 to the minus 3 molar per second, into this expression, we will get the following answer. 2/3 times 6.5 times 10 to the minus 3 molar. That will give a final answer of 4.3 times 10 to the minus 3 molar per second. This answer makes sense because in the same time period, 4 moles of ammonia are being consumed as 6 moles of water is being produced. Therefore, the production of the water will occur at a faster rate than the consumption of the ammonia.